As you recall, I actually told you in one of my videos that next video is going to be covering about linear algebra and analysis problem sets. The problems here are actually really, I think, unique and quite niche in some sort, because they're taken from some major competitions that we're probably never going to encounter. Uh, but it's actually generally easy to know. You can actually go to Evan Shen's napkin book. It's actually freely available, and I really recommend it to people who actually want to study mathematics as in general and how to have a bright grasp of the basics on every field of mathematics. But for now, I'm just gonna cover some basic analysis problems and maybe some linear algebra terminology. I think it's better to start from linear algebra, since I guess the analysis course is taking after that, but we're gonna return to analysis later on in this videos. So, okay, so what is linear algebra? Probably lots of people has asked me what is linear algebra. Well, it's not mx plus b in some sort. Well, technically it can be, since there can be a bilinear mapping of some sort. But uh, let's say I'm okay, I'm normal. I have friends. Then the normal occurs is that linear algebra is the set of is a study of vector spaces and linear maps, and how those conjugates actually work with together. Instead of having the finite set of normal and arbitrary functions, we can actually define a set, let's say a three-dimensional plane. And what it does, linear algebra is study of vectors and directions in some sort. So um, then let's just walk through some problems. Yeah, I guess some of the problems shouldn't be that hard. So I guess I'm gonna cover some basic terminology. I guess okay. So let's go. So well, first of all, what is a matrix? A matrix, you're probably familiar from high school, since matrices are, I think, not commonly learned in high school. I've never seen it in actually in high school programs, but generally, matrices are usually covered there. And what is a matrix? Is a matrix is a usually people tell that it's a box of numbers. Uh, a box of numbers that's defined as a certain operation, but it's actually really hard to explain matrices without the proper knowledge of vector spaces. So I'm gonna explain what vector spaces are. So vector spaces are in general are some arbitrary functions in some sort. Let's say my vector space V. It's in the set of R11. It means that my all of my diagonal entries are gonna have one sort. So here is my matrix. Well, it's not actually a matrix; it's just a singular value. The same here applies. For any vector space is a functional operation that holds every possible vector in it. So what it does is we essentially have a set of operations that are acting on this vector space and can only act on this vector since it creates some certain properties in the vector space. There is a fundamental understanding of what is a group. A group is a functional operation that holds for all integers. Let's say when you learn basic addition, you're probably familiar with one plus sides, and y is 2 plus 1 is equal to 1 plus 2. Well, in groups in particular, you can actually find some arbitrary functions here. So one plus 2 is equal to 2 plus 1 because of the what's known the commutative property. A commutative property, what it does is, a commutative property is a property that defines a set of numbers a by the binary operation b such that is equal to b times a. The order doesn't matter. The same for associativity. Associativity, it says for any binary operations b times c, it doesn't matter where you put the brackets. The operation is gonna be still the same. The same for here. Now for I think for matrices in particular, a matrix is a fundamental operation in linear algebra that defines the set of vector space and acts of all of the numbers in vector spaces. It's I think from the computer science perspective, a matrix is a uniform of all of the variables that are stored in the vector that can be manipulated. For example, there are two types of linear algebra: linear algebra from the proofs perspective, and some computational linear algebra. Uh, Honestly, you just study what's best for you. I would say probably say computational is more interesting than a proof linear algebra because it deals more with applications of linear algebra and how can be used, and generally some of the problems are just much more interesting unless they're hard ones. Now for I'm not saying hard ones are not interesting. Is that the proofs perspective problems are much interesting, I would say, in my opinion. But what is a matrix? How do you define a matrix? So let's say define a matrix A such that it's n times n. N times n meaning there's like n entries on the columns and n entries in the bottom. So we define by the real set of numbers. Real entries. Then we have, let's say, uh, 1, 1, 1, 1, 1, 1. Some set of operations. This is a matrix. The certain property you actually need to know is systems of linear equations. When you open any linear algebra book, you can actually find that the first topic you learn is how to solve systems of linear equations. And I guess you're wondering, I did this when I was in fifth grade. Well, why would I spend my time to actually put some plug-in numbers? Well, technically, this is actually really fun. Why is linear independence? Why is linear combinations are actually interesting in linear algebra? Because the set of matrices are actually deal with this particular sequence, and to deal with this arbitrary function, you need to define some sets and uh, find theorems of these axioms. Now, the crucial thing is that let's say we have the set of vectors v1, v2, v3. And let's say there's some constants, s1 plus c2 sv2 till is equal to 0. So let's say a linear independence, what it is that if the equality here occurs for linear independence if and only if c1 is equal to c2 is equal to 0. All of these diagonal combinations are equal to 0. And linear dependence is just the opposite of this. There's some interesting properties here that I want to underline, but certain commutations cannot be done. So yeah, so the crucial thing to note is that linearly independent matrices have their linear maps are actually equal to 0. So yeah, I think that should be it. So probably I'm gonna cover some van der Moder determinant and general determinant problems if I have space here. I guess wait if I can find somewhere here. Never mind. So yeah, never mind. So I'm gonna teach what is a van der Moder determinant. Van der Moder determinant is a determinant with diagonal entries of 1, x1. Let's say x1 is just a sequence. x1 squared till n times for x1 n minus 1. The same applies here for 1 x2 squared 1 2 3. Okay, so 2 n minus 1, and this pattern continues 1 x n for xn minus 1. So the determinant of this, define a van der Moder determinant. Let's say there's a matrix V in some vector space. So in matrix V, a determinant. Okay, determinant. What is this? Okay, what's a determinant in general? A determinant is a functional operation that defines the change of the area in a finite set according to the linear map. This is actually, I guess, it's more arbitrary than I actually realized, but there's some sense into it. Is you can watch some three blue one brown videos about I think how to visually interpret all of the data, but I'm just gonna talk as determinants as this. Wait, so before we step into what the remote determinant, let's just go what's an eigenvector and eigenvalue. So define an eigenvector and an eigenvalue of the set of operations is that such that for any matrix A in the set of n times n, if you can find some matrix X such that is equal to some lambda X. So what does it mean? Like Emir, okay, explain yourself. What is this? Uh, we know that you don't have life. Okay, so basically what it does is if you can find, so lambda is called an eigenvector. Some arbitrary function is that such that the operation holds, and x is just an eigenvector. Some vector in k vector space such that multiplies for this vector we actually can actually have the equality. This is what is called the eigenvalue decomposition. If you can find some arbitrary function here, then it's just pretty simple from there. Yeah. Now, so probably let's just go. I guess. Uh, Now, how do you find the eigenvector? Well, you can actually find, let's say, the determinant for 0 for matrix A. You can find that such that, let's say, D, you can write it as A, or you can just Cholesky decomposition, but I don't think it's necessary here. Lambda, and by finding this, we set this polynomial equal to 0 and find some values for lambda. And the I think interesting property to know is that m minus 1 d, where m is a where m is a diagonalizable matrix is equal to A. This is what's called eigenvalue decomposition. There is also more into a singular value decomposition than other particular vectors, but I'm gonna cover that. I think you can cover that by yourself since it's not really important here. Now back to our wonder mode determinant. Here it holds the interesting property. It's actually equal to phi. Let's say 1 is less than or equal to I is less than or equal to J is less than or equal to N. And it's the polynomial of some degree of xi of xj minus xi. This is our determinant. How does this work? We can create a multivariable polynomial p, and then if we can prove that all of the vectors are there, do not cancel each other, then we're just practically done. Now, okay, I guess let's do some problems then. I guess so. Let's do the first one, the Putnam. 19. I'm not sure some of the problems are Putnam level, since I think they're not actually taken from real Putnam, but they're like Putnam style questions. So let's do some problems. Okay, I'm just gonna do run the problem. I guess. Okay. What problems should I do? I think no. These are actually bad examples to do for problems. I'm gonna give you one more. You actually a trace of a matrix is diagonal sum of a matrix. Okay, now my problem is that do there exist some matrices X A and B such that we have that A like they're n times n matrix B minus B A is equal to I. Okay, try to solve this problem. Well, you can't. I guess so. Okay. Now, what is it? Okay. So here, what is the fundamental property here is that we can actually find some function value. We can actually put the trace here. A trace of BA is equal to AB, and it can't if we minus the trace of this variable, it can't equal to the identity matrix, since identity matrix holds for all values n, and n is clearly greater than 0 for all diagonal matrices n times 1, 2 times 2 and more. Okay, Now, done with linear algebra. I guess you already know it's analysis, right? So I'm just gonna do the last problem and probably do other problems later if I have time. And I guess it's a bad idea to do it at 12 p.m. But pretty useful, guys. Now here, like people would actually think, what is this? Did you have amnesia where you were struck? Well, it's actually pretty fun. You know that the definition of an integral is separating a particular function or variable or into several partitions or infinite amount of partitions. We can use a Riemann integral to actually evaluate this. So as n approaches infinity, we can prove that from 2n till 1n, n plus I, we can actually find some log value. So here is from n. So it's just an integral from n plus 1, n plus I, let's say n plus I, well, let's say n plus x, from n is equal to 2n, n is equal to n, 1. Here, yeah, this is just ln plus x, boom. And now as n approaches infinity, we can actually say that ln 2 n minus ln n plus 1. Here it just cancels out really nicely because, okay, so actually the idea is wrong here, since if we're doing from partitions, it should be just 1 over x, and just 1 over ln x just cancels out because 1 ln 2. So 1 ln 2 is the correct answer. So thanks you. I hope it was pretty fun. I guess this is the only experience. I'm gonna try to do a better handout next time, since some of the problems are too hard here, I guess, for everyone else. So bye. I hope you got catch you guys later.